This call is now being recorded.
Hi, welcome to the next session. Today we are going to cover the hypothesis testing. Earlier we had covered all these topics, importance of stats, basics of stats, center and spread of the data, probability, conditional probability, random variables. We covered distributions, binomial normal distributions, sampling and central limit theorem. And then last session we talked about confidence intervals. This session we are going to focus on hypothesis testing. And actually, it is important because in real life scenarios, we find this to be very important. And it's all there in pharmaceuticals, government, business, and all of them. And basically, it revolves answering the question. I mean, whatever, let's say there is an experiment in which we have made some observations. So the question that we try to answer is, could these observations really have occurred by chance? Right? So that is the importance. Now, give me a minute. Yeah. Now let's begin with an example from law. Okay. To give a bit of background, so there were, back in the early days, there was huge discrimination between African Americans and the Native Americans. So, this particular example focuses on that, and f- on the cases argued between 1960 and 1980. So expert witnesses presented the case for racial bias in jury selection. How? Let's see how. So panels of juries are theoretically drawn at random from list of eligible citizens, right? This is supposed to be the norm, right? That there should be a random selection. However, in the southern states in 50s and 60s, new African Americans they were found on jury panels. So jury panels are the panels or a group of people who decide on a case or hearing all the facts and all. So there were very few African Americans on the panel, so some defendants challenged the verdict, right, stating that it's not statistically right because some facts they stated were 50% of the eligible citizens were African American, right, for that southern state, um, to be precise, and uh, for the jury panel of 80 people, only four were African Americans. So these, I mean, considering these facts, it seems like probably the juror panel is biased, right? Let's see if it could be result of a pure chance. Let's see how we can do it statistically. For the sake of argument, let's say that the selection of potential jurors were random. So that means that amongst, I mean, since we are going to pick 80% jury, so it would be like an binomial random variable with 80 trials and p is zero point 0.5 because they are equally distributed within the population. Now, the lawyer argues that the chances of getting a jury with only four African Americans, which is probably a probability of x less than equal to four. This comes out to be a very small number, 0.0000, so on, 1 4, right? So he says the chances are very less of getting jury member less than or equal to four. So then he argues, since the probability is so small, that then there is a strong evidence against the hypothesis of random selection, because when we hypothesized we said that it's a random selection. In random selection we have the equally likely probability. Now again he makes a comparison, he tries to identify the similarity so that people can understand that these chances are much lesser than the chances of getting three consecutive royal flushes. So getting royal flushes, I mean, a flush is a combination of five cards: ace, kings, queens, jack, and tens. And getting three consecutive royal flushes is a very um, small chance, I would say, and the probability of getting an African American is even lesser than this. Yeah. So the judge rejects the hypothesis of random selection. Right now, let's see. Before this, let's see one example in Excel. For this, for the same experiment that we just saw, uh, let's say this the probability of selecting an African American was 0.5 because it's equally distributed. The number of trials is definitely 80. Um, Now, for a Bernoulli trial, we know that for k number of successes, having p probability for success, the probability is nck into p to the power k into 1 minus p to the power n minus k. So, on the same lines, we calculate the probability of k, that is number of successes. Now, k is going to be a random. K is going to be a random variable, binomial random variable, and the mean of this distribution. I mean, we can see in this that the probabilities are maximum. That depends on x, and they are around the mean value 40. So once we calculate the mean value, which is np for a binomial distribution, the mean comes out to be 40, variance is 20, and standard deviation is the root, which is 4.4. So now what it means is that the mean of the African Americans which could have been selected, which should have been selected based on the based on random experiment, random selection, it would have been 40. And the standard deviation of amongst in that random variable could have been 4.4. Let's see a different view. Okay, let's say in column E in this table you have standard deviations, and if we consider one standard deviation, so one standard deviation meaning uh, mu plus sigma to mu minus sigma, or mu minus sigma to mu plus sigma. So basically, one standard deviation below the mean and one standard deviation above the mean, right? So we have a minimum and the maximum value of x, right? The minimum value of x is x minus sigma, maximum is x plus sigma. So same thing here. The formula is we just are counting the number of standard deviations so that it is uniform, right? Now we have the x minimum, x maximum. Now, since it's a normal distribution, so we can have the F score as well. So F score corresponding to this minimum value of X is 15%. That is F score corresponding to 35.53 is 15%, 15.87. And F score corresponding to 44 is 84.13%. Now, now we already know the F scores, right? To get the probability of X between minimum and maximum value, or z minimum maximum value, we just subtract the f scores, and we get 68.27, which is already which we already know for standard normal distribution. Sorry, for standard normal distribution, almost 68% of the values, they lie within one deviation, one standard deviation from the mean, right? And in column L, you just have the area or the probability that x doesn't lie between 35 and 44, right? Same way, you will see that if you consider two standard deviations, then the lower upper values are 31 and 48. If you consider three standard deviations, 26 and 53. So three standard deviations is a very good approximation. I mean, if you look at the probability, there are 99. The probability of x between 26 and 53 is 99.73%. Now our observation is that x is less than or equal to 4. If you see here, right, you don't even see up till 7 standard deviations, you don't even see 4. Moreover, up till 8 standard deviations also, you don't see 4. It's between 4.2 and 75.78. Now, this becomes clear that probability of x less than equal to 4 is going to be very less, right? and we also saw it, right? It's 0.00, I mean 10 zero something 14. If we plot the same, on x-axis we have the x's or the number of African Americans, on y-axis we have the probability. So definitely we are going to have the maximum probability for n is equal to 40, right? And we will have I mean, this blue area though, or the blue bars that you see are within one standard deviation. Blue plus red is within two standard deviations. Yellow plus red plus blue is within three standard deviations of the mean, right? So uh, we know that the since the probability of x less than equal to 4, it is I mean, if you take the minimum value of 4 and maximum value of 80, then you will get a f score of almost 0%. I mean, excel is not able to figure this out. This is such a low value, right? Now let's do one thing. Our null hypothesis, or in our original hypothesis, what we said is that the selection is random. Okay. Now let's say, when would this data had made sense? If let's say if I took a p as a 0.2, right? So in that case, I can see that within four standard deviations, my um, observed value, x less than equal to 4, it would fall in this value, right? And this probability that I have, the fz for x less than or equal to 4 is 0.04%, right? So but the standard value of p, which is 0.05, uh, it's still lesser than that. So that is why, I mean, if even if every 2 out of 10 were African Americans, this wouldn't have made sense. But if it was 0.1, yeah, definitely it would have made sense, right? So this is a possibility. Now let's see how the default numbers, or the how default p values are defined in the industry. Let's for this hypothesis testing, let's follow a process, and let's state some formal steps. First will be, we need to formulate all the hypothesis. All the hypothesis is h naught. First is h naught. H naught is the null hypothesis, which is usually that the observations and are the result by chance. I mean, it's a purely of chance. And there is another hypothesis, alternative hypothesis, HA, and it is that there is a real effect, and that the observations are the results of the real effect plus chance variation. In the court case, H naught says the jury was randomly chosen, and hence the probability p is equal to 0.5. Right? This was my H naught. HA, which is alternate hypothesis, it says that African Americans are less likely than their proportion in the population to be selected for jury panel. Right? So HA is p less than 0.5. Step 2 in hypothesis testing is the test statistic. We need to identify some statistic that will assess the evidence against the null hypothesis in favor of the alternate hypothesis. For example, in the court case, the test statistic is the binomial random variable with p of 0.5 and n of 80. Right. Now, step 3, it's a important step, p value. So think of p value as a probability statement which would answer the question that if the null hypothesis were true, then what is the probability of observing a test statistic at least as extreme as the one we observed, right? So this assumes that if the null hypothesis was true, so what is the probability of observing the test statistic at least as extreme as the one we observed? Right? In the example, the p value taken, it was, I mean, the p value that we got was 1.4 into 10 to the power minus 18. Right? Again, this was calculated using modern computers. Next step is we need to compare the p-value to a fixed significance level. This is important. Fixed significance level alpha. This is something that is already defined, and it acts as a cutoff point below which we can reject or accept a null hypothesis. Now, in the jury case, the statistician took the alpha to be 3.6 into 10 to the power minus 18, right? And the chances of being dealt three royal flushes in the row, right? This is the example that he gave. And the null hypothesis, which was random selection, it was rejected, meaning p-value is greater than alpha. Yeah, the p-value, as we saw, it was the order of 10 to the power minus 14, so it was greater than this. Now, usually you will see that we have a fixed alpha level of 0.05 or 0.01, right? And actually, it goes back to the pre-computer era where we had to use tables and all, reference tables and all for everything. So it became a practice to use the p-value of 0.05. Now let's see a scenario where we need to do the hypothesis testing on a large sample, and we need to have significant test for proportions. Okay, in the jury example, this case is a generic problem, and this was a special case actually, and the null hypothesis was of the form p is equal to p naught, right? And p naught was some probability in this case. I mean, in the jury case, it was 0.5 because there's a equal population. Now let's look at some generic example. Right? Let's look at some examples where the hypothesis is p is equal to p naught. If you remember, we covered this example where Sherlock Holmes was a pollster and he wanted to see the chances of winning of Senator Astute. Right? So they observed a large sample, but they observed around 1,000 people, and they calculated the probability p cap. Right? And p cap was 0.55. They obtained, and obviously the winning majority is 0.5. So what he wants to know is what are the chances that p greater than 0.5. In this let's do it with hypothesis testing. In this, the step one is we state the null hypothesis h naught p is equal to p naught, right? Alternate hypothesis, it depends on what we are looking for. What is our problem statement or the objective? In Senator Astute's case, alternate hypothesis will be p greater than p naught, right? Uh, but in other cases, the alternative hypothesis might also be that p less than p naught, p not equal to p naught, and so on. Also, in our jury selection example, the alternate hypothesis was p less than 0.5, right? And sometimes we are interested in knowing if p is different than some value p naught. So in that case, alternate hypothesis becomes p not equal to zero point 0.5, something like this. Step two is determining the test statistic. It is, let's say, z obs is equal to p cap minus p naught upon standard deviation, p naught into 1 minus p naught divided by root n. This is the standard error. So this will measure how far p is deviating from p naught, right? This z is because we have a subtraction term, right? So this measures how far is p from the p naught. Step three is the p-value, right? Now the p-value will depend on which alternate hypothesis is relevant, right? So based on these conditions, the p-value can be right-handed. Your alternate hypothesis can be right-handed, where p greater than p naught. In this case, p-value, p probability z greater than z ops will be used. If it's left-handed, then alternate hypothesis p less than p naught. It will use a p-value of z less than z ops. If it's two-sided, it will use a p-value probability z mod greater than z ops mod, right? Something like this. So here we have this area, Here we'll use this area, and here we'll use a summation of this area and this area. In case of Senator Astute, let's talk about Senator Astute. So how the steps or the steps in the hypothesis testing um, full result, I mean, what results do they give, right? So the hypothesis in case of Senator Astute, or null hypothesis, is p is equal to 0.5, and alternate hypothesis is p greater than 0.5, right? So and the test statistic we formulate, it is 0.55 p cap minus p naught 0.5 upon p naught into 1 mass p naught divided by under root n. So this is 3.16. Now let's see the probability z ops. So probability z greater than z ops observed is probability z greater than 3.16. This is 0.0008, right? So this we have gotten from the normal table. Now let's interpret this. So he's being fairly conservative, and he takes a significance level alpha of 0.01, and what he sees is that this p value that we obtain, it is lesser than alpha. So what do we do? So p value lesser than alpha, we reject h naught, that's it. So they reject h naught, and once they reject h naught, they will have to accept the alternate hypothesis. And our alternate hypothesis suggests that the population mean is greater than 0.5. So in a way, he's saying that you will win. With a significance level of 0.01, I can say that you will win the election. Now, let's consider this example. Okay, in this example, we have a large sample test for the population mean. Okay, and this is used mostly in inspection sampling, which is widely used in the industries. Let's say there is a manufacturer called New Age Granola, and they claim that the average weight of the cereal boxes is at least 16 ounce. But the genuine grocery corporation, they are saying that they will send back the shipment if average weight is any less. Now let's see what the grocery corporation does. So they choose their hypothesis. Null hypothesis is mean is 16 ounce. Alternate hypothesis is mean less than 16 ounce, because mean, if the mean is greater than 16 ounce, that then it is well and good for them, right? And if they reject the null hypothesis, then it means they reject the granola. Next is that they choose a test statistic. So I think this is pretty clear now. The test statistic that we form, x bar minus mu naught upon standard error, which is s by under root n. S is going to be the standard deviation of the sample, right? And moreover, we already know that if n is large enough, then it would approach to a standard normal distribution using the center limit theorem. They again, to calculate the mean and the standard deviation, they pull out a random sample of 49 boxes, and they determine the stats as follows. X bar, the mean of the sample is 15.9 ounce, and the standard error is 0.35 ounce, right? So I mean, initially we can see, okay, probably this is a understatement, or this is an exaggeration that the weight is going to be 16 ounce. But let's see what the hypothesis testing tells us. Now we plug these x bar and s values in the test statistic, and we obtain the z ops, which is -2. Now they again, the step 3 is computing the p value. When we compute the p value for h naught, it is 0.0227, right? Now this is less than 0.05, right? So what do? Reject the null hypothesis. Null hypothesis was that the mean is 16. So once we reject it, we need to accept the alternate hypothesis, which is mu less than 16. So they say that we won't accept this, you can go away, and they reject the shipment. Now if you see here, right, if your x bar it was greater than 16, or let's say some value greater than this, uh, probably 16.5, then this value would have been positive, right? And considering this value as positive, if it was somewhere here, right, then you would have looked at this area. And if you looked at this area, this was probably would have gotten into your p value limits, and in that case you would be able to accept the null hypothesis, that is accept the shipment. Moving on, so let's talk of another example where we have a very small sample, and we want to test for the population mean. Okay, and for this, let's say we have a company called Chameleon Motors, and there is a crash test that they do. They try to crash all the vehicles, testing vehicles under to some obstacle at 10 miles per hour. And the righteous insurance company is saying that they will insure an auto only if the mean repair cost after a 10 after the collision is less than $1,000, right? So now what the company does is they want to estimate the chances, or estimate the probability using a significance level. So what they do is they define a significance level, standard alpha, which is 0.05. So then they declare the null hypothesis, which is mean greater than equal to 1,000. Alternate would be less than equal to 1,000, because this is the favorable one. HA has to be your favorable one. So mean cost is okay. The test statistic is going to be the t distribution. The reason is that this number of samples are small, because it's a crash test, right? You can't have a big sample for this. So it will be a t distribution. And mu naught is going to be your hypothetical mean, which is 1,000. Again, we have 4 degrees of freedom in this. So 5 observations then. And we want our observed t value to lie to the left of minus t 0.05, right? Because low value of x bar is desirable. Shear, right? Low value is desirable. So x bar minus mu naught should be negative to support h alternate hypothesis, right? So that again depends. I mean, see, that is why we need to clearly state the null hypothesis and the alternative hypothesis, right? X bar low. If x bar is low, then x bar and mu naught should be negative, right? This will come out to be negative, and this will support my HA. This is the table for the alpha values and the degrees of freedom for T distribution. And at a significance level of 0.5 and degrees of freedom, we have the T value as probability of T as 2.13, right? So we decide to reject the H naught. Why? I mean, we will again calculate the T obs, which is minus T 0.05, and this is minus 2.13, right? Um, and we had earlier seen, I mean, probably you can assume these values that x bar is 540 and the standard deviation of the sample is 299. So what they do is they put it into the formula for the test statistic, and test statistic becomes 540 minus 1000. 1000 is the mean that they have taken in the null hypothesis, divided by s by root n, right? So they get minus 3.44. Now this value is lesser than t obs minus t 0.05. What does it mean? That you reject the null hypothesis. Moving on, let's talk about decision theory a little. Um, we can think of hypothesis testing as and you know in terms of household smoke detector, right? And the results, how do we infer them? All these significance test and the hypothesis test, right? Let's say, I mean, I hope you all know how a smoke detector works. So it's a kind of an indicator or a sensor which is fitted into the ceiling, and it detects smoke, right? Um, so whenever you burn a toast, probably it will go off. Now, what there are two types of error. I mean, if you consider the scenario in which, let's say, fire is happening, not happening, alarm is ringing, not ringing, so then there we have two types of error. Either everything is fine, okay, fire goes on, alarm goes on, all right, so that is okay. Fire is not there, alarm is not there, that is also okay. But now, if there is some error in something, or let's say in the alarm, right? If it's a false alarm, if it's a true alarm, then we have two different types of error. One is type 1 error, that is, alarm will go off without a fire. And conversely, we have a type 2 error in which there is a fire without an alarm. So you can remember this. Type 1 error is alarm without a fire. There is no cause, but the outcome you see is positive. And we already know, I mean, type 1 error is very simple. We just turn off the alarm, we remove the batteries, right? But this will increase your type 2 errors. Even if there is a fire, since the batteries are not there in the alarm, it won't go off. Now let's summarize this, okay? As I said, right, if there is no alarm and no fire, then there is no error. But if there is no alarm and there is a fire, it becomes a type 2 error. If it's an alarm, if there is no fire, it becomes a type 1 error. If there is an alarm and there is fire, then it becomes no error. So this is your decision table. And you can think of it as the null hypothesis. I mean, you can think of null hypothesis as a condition of no fire, while the alternate hypothesis is that a fire is burning, right? The alarm corresponds to rejection of the null hypothesis, right? So this is, I mean, if this is your true state, if this is your S naught, H naught, and this H naught, which is null hypothesis, and the alternate hypothesis, then for no error, you have to accept H naught, and alternate hypothesis, you have to reject H naught or accept HA with if there is no error. And again, I mean, you will reject H naught if type 1 error, you will accept H naught if type 2 error. So this brings me to the end of the session. I hope this was informative. Please let me know your feedback on this, and I will definitely try to work on it. Thanks.